good morning or afternoon. I'm here to talk to you about taking control of your project. We're going to do that with the cost and schedule risk analysis. My name is Brian Putt. I worked for 4 decades at Chevron and spent 2.5 decades doing decision analysis and helping develop a cost and schedule risk analysis model that could be used internally. So today we're going to talk about why is cost and schedule risk analysis important? How does decision quality relate to the CSRA? And what are the inputs to a CSRA and how are they used? This is a real difficult question that came up when we conducted a interest group on the CSRA through the Society of Decision Professionals. If you're not a member of SDP, you might want to check that out. And then we're going to go through an example of building a house. We're then going to incorporate mitigation and have some conclusions and feedback. So why is cost and schedule risk analysis important? Well, overruns are common in infrastructure, buildings, technology. For IT projects specifically, a 2004 study found that there was a cost overrun of about 43%. 43%. 71% of the projects came in over budget, exceeding time estimates, and had estimates that were too low, too narrow in scope. In the IT projects, I think the issue there is they keep changing the scope. They keep changing what they want or don't want in their projects, and that's why they tend to cost overrun and also run behind schedule. In total, there was a waste of $55 billion in the US alone. So what are some examples here? Here is a destroyer that was commissioned by the Royal Navy. And they initially said the ship was going to be commissioned in 2014. The reality is it didn't get commissioned until 2017. And so there was like a 3-year delay, Let's talk about ExxonMobil. In June 2018, they acquired an interest in an offshore block in Brazil. And they are expecting to be on production in 2023 or 2024. Well, obviously, we're not there yet, so we don't know what the actual outcome is. But then later on, the Brazil oil and gas, they said it takes 8 years of exploration to get to a point where you're making a development. So then if you add on a few years for actually doing the construction and bring it on production, you come up to a 2029 timeframe. Now they're 5 years late by my estimates. Well, we'll have to find out what happened actually. NASA cost overruns in June, article from June 15, 2018. This was a really long project to put a man on the moon. And one of the biggest problems here is probably by the way they established a budget. And they use something called a joint confidence level, JCL. And I think we're going to talk about that a little bit later, perhaps at the end of the session, okay? And in the NASA project, there was a constant culture of optimism. And this is true in every project. There's always going to be optimism. That's our nature as humans. We're always optimistic. That's why we need unbiased estimates. So why do projects fail? Well, let me just hit a few of these. Inadequate initial scoping. We really need to do a good framing session to understand what is the scope of what we're trying to assess here. Requirements are unclear. What do we really need in this project? What's necessary? What is gold plating the project, okay? Continuous and unconscious biases or conscious and unconscious biases. I've already talked a little bit about that, but it's going to be prevalent in everything we do. Also, we have down here the unaligned expectations. What are the expectations of management? What are the expectations of the project manager? What are the expectations of your joint venture partners? And failure to get sign-off from impacted organizations after framing. So we need to get the management, we need to get all the organizations that are involved have to sign off on the frame of the project. Okay. During the execution phase, we find that oftentimes the supplier skills are overstretched. There was an earlier presentation in the Risk Awareness Week that talked about this as well, where you get multiple projects and there's hyper escalation on the skills. There's just not enough people. And I think Chevron experienced that when they tried to do 2 LNG projects on Western Australia. There are risks that are unidentified or not managed. So if they're not identified, we need to kind of stop and figure out how to mitigate them. And if we don't manage the right tasks, then we're going to be have a problem too. And the cost and schedule risk analysis can help us on that, identifying what's important. We can have scope creep. In other words, we keep changing the scope of the project. Really bad idea, really bad idea. And we get measured against an unrealistic time schedule and budget allowance. So if I say I'm going to get something done in 2 years and it's really going to take me 2.5 years, what am I going to do? Well, I either have to give up on the schedule and try to stay within cost, or I'm going to have overtime and everything else to try to meet the two-year schedule I promised. So having some realistic schedules, understanding that the schedule that I appropriated, in other words, I came in with an appropriation request and I said I was going to get it done in 2 years, and people assumed there was a high probability. I'm not sure what high probability is, but management says there was a high probability I'm going to get it done in the 2 years. Well, in reality, maybe there was only a 30% chance you'll get it done in 2 years, and 70% chance you're going to be behind schedule. So getting something realistic, I think, is really important at that time you're doing the appropriation request. Management needs to understand what's realistic in executing this project. So the objective of the cost and schedule risk analysis is to come up with a distribution for the time required, as shown over here, and for the cost uncertainty. The orange lines here represent the baseline values. In other words, when I go to let's talk about cost perhaps. If I go to the cost engineers and ask them how much each of the components can be, they're going to give me a number. And that's the baseline cost if I added up all those numbers deterministically. And they're going to tell me how long it takes to do, and I get a number over here, okay? So let's talk about the decision quality. So there's the DQ spider. We're going to start up here. We have relevant decision framing. Are we addressing the right problem? So we need to frame our CSRA. How big do we include here? Are we going from feed? Are we going from FID? What is it that we're trying to frame here? Do we have a good set of alternatives? Well, we might have to do some mitigation along there to look at some different alternatives. We may have to do the CSRA on multiple alternatives that are being generated during phase 2, the generation phase. Relevant, reliable information, okay? And understanding the consequences and trade-offs. We're going to trade off cost versus schedule. Is the analysis logically correct? Well, we're going to see a Putt diagram here that's going to show the relationship of the activities, and that has to be right. And are we ready to execute the decision? So we need to work on all of these even during the CSRA. So when should a CSRA be conducted? Well, there's multiple phases of the project. There's the vision of the project, and there's scoping economics. Then we go into a project selection period. There's front-end engineering, FID, and project execution. This is kind of more oriented towards an oil project, but I think it applies to, a construction of an apartment or anything else that you might do. In pharmaceutical, they have all kinds of phase trials. And really, the CSRA can be conducted in any one of these phases, Having a good idea how long it might take you to get the project online early on may set some realistic expectations of management, rather than being really optimistic and then having to come in later and say, well, it's really not going to be, 2024, it's really going to be more like 2028. So before we get into looking at the CSRA itself, let's do a little bit about statistics. Let's talk about asymmetric distributions. So here's an asymmetric distribution. It's asymmetric because you see this mode here is over on the left side relative to the total range. And this is the cumulative distribution function of this probability distribution function. So if I just integrate it, if you will, I hate to use integration because that's one of those red words from Sam Savage. But if I just add up the areas as I go across here, this is what I get. So what I can tell here is that, now let's look at this 10, value of 10. There's a 10% chance that I'm going to be less than 10. Let's pick on this point here. There's a 20% chance I'm going to be better than, let's call that 27 or so. So that's how I can read this. It's more difficult to read those kinds of numbers here off the PDF, which is the reason I love the cumulative distribution functions. The mean or expected value or the average is a common metric, but is not necessarily the P50 or the median. So for example, in this particular distribution, and this is pretty common, the median or the mean of the cumulative distribution function of this distribution in total is really about the P60. You can see it's not here at the most likely outcome. That's probably the next one here. Now, here's the modes, the most likely with the highest density. That's right here, and it's represented by the portion of this curve which is the steepest slope, right? But we normally don't need to worry about the mode. More likely we're worried about the expected value. And then the percentiles reflect the probability of being that number or less. We've already kind of talked about that. And so here I've clearly showed the P10 and the P5, P95, P90, and here's the P50. So you get the idea. Just want to make sure that we get the right terminology, because if we get the wrong terminology, then we have difficulty assessing ranges. So then the question becomes, if I'm doing the CSRA, what input should be assessed by the subject matter expert? This is an area with a lot of disagreement, because we can go with the minimum, most likely, and maximum, which generally generates a PERT distribution or a triangular distribution. We can do a P10, most likely, and P90, a low, most likely, and high. This is really generic. You got a P10, 50, and 90, and you got historical data. I love the historical data. I think that's a really good answer, and I think particularly with the data science movement today, companies really need to be collecting historical data on their own projects, because they have a lot of projects, and then doing some data science on that to say what is the appropriate historical data that would apply to this particular project. There are three main outputs for an analysis. One is the cost contingency, the cost risk reserve, and the schedule contingency. So what is cost contingency? Well, the AACE is defined cost contingency as an amount added to the estimate to allow for items, conditions, or events for which the state, occurrence, or effect is uncertain, and that experience shows will likely result in additional costs. They would exclude, however, major scope changes. We've already said scope changes are bad. Extraordinary events, management reserves, escalation, and currency effects. Contingency is expected to be spent on a project. Cost contingency is generally the difference between the baseline value and the CSRA EV result. So here is a distribution where this was our baseline. We came up with this as our total cost estimate based on the uncertainties that have been assessed. And so the difference between this baseline and the expected value would be that contingency, in this case, 59. The issue is whether cost contingency is already included in the individual cost estimates. So we need to caution our subject matter experts not to try to add in this contingency as they give us estimates. Also, the question is, should strikes or natural disasters or other rare events be included in the analysis? And generally the answer is no. However, I will suggest that, let's say that you are trying to move a platform or something, from the shipyards in Korea, to the Gulf of Mexico. There may be weather conditions that would not allow you to move that ship safely with the platform on top of the ship, and therefore there may be a finite discrete time window where you could actually move it. So it may be really important in order to include weather in your CSRA, but it's going to depend upon the analysis that you're trying to do. So what is reserve estimates? Risk reserve. Risk reserve is something referred to as management reserve or owner's reserve, and is a portion of that capital budget used to cover reasonable unforeseen events. It includes costs for events that should they occur, it would be expected that the budget be able to cover these costs. For example, including weather, equipment damage during the construction. It doesn't include, however, tornadoes, acts of war, or other events. Scope changes are still outside escalation and currency effects. We'll add the escalation and currency effects separately. The currency effects and escalation are going to be something that's going to be dictated by the corporation, what should be used in the analysis. If all goes well, we don't need to use the risk reserve. What is schedule contingency? It's an extra allowance of time on a project schedule to ensure that you have a reasonable chance of completing the project on time. No sense in giving an estimate that assumes only a 30% chance to getting there. I mean, what happens when you exceed the schedule? You've got more manpower, you've got more cost. Not only should you have contingency on the total project duration, it should also be added to any kind of milestone on the project. This includes reasonable risks that should be expected to budget for. Usually excludes extreme risks and, once again, scope changes. Just want to eliminate those scope changes. If all goes well, you may not need to use all or even part of your schedule contingency. So we talked about what inputs we would use or assessed by the subject matter experts. And then we need to decide on the distribution. So we have the triangular distribution, the Putt distribution. There's something called the trigen. There's a Meyerson. There's a Metalog distribution, which is really, really flexible, available in SIPmath. That's available from probabilitymanagement.org. Maybe no distribution. I'm not sure what that means, really. Adjustments to the SME assessments based on historical data. So I think there's lots of things that could be done, and there's advocates for each one of these. There's no right or wrong way. The question really becomes, does it matter? Does it really matter? So let's compare some of the distributions. Here's a Putt, a triangular, trigen, beta, and a Meyerson distribution, all shown here. All are using the same random numbers, okay? This was all done with SIPmath, by the way. And the triangular and trigen have the same result. Beta is a function of the scope parameters. Putt is a transformation of the beta distribution. The Meyerson has a really long tail. But all the EVs are similar other than the Putt distribution. We can see those EVs over here. So the Putt distribution is 53. All the others are in, 61 to 64 range. And does it really matter if we're that close? Does it really matter? Most important is that the SMEs know what parameters they're trying to assess and what is to be included in the analysis. In other words, they're not trying to include contingency. So let's talk about a flexible CSRA model using Excel and SIPmath tool. Remember, SIPmath is available from probabilitymanagement.org. This model we're going to look at requires no macros to run, uses a data table to calculate the trials, and uses standard Excel graphics editable by the user. So the features of the SIPmath model, we won't talk about all of them, but it has complete flexibility to reflect task relationships. This is really important, okay? And and flexibility to use inputs other than the P10, 50, 90, such as the Putt or triangular. The graphics are easily copied to PowerPoint, Word, or other applications, because one of the things that's really important here is great to do a great analysis, but unless you can talk to the decision makers and explain it, most likely with graphics, not equations and just bullet points. And SIPmath makes it really easy to generate these graphics. You can add explicit mitigation with probability of success. One thing that can happen is the project manager says, oh, I can mitigate that problem. Why don't we do this? And yes, you can put that in the model, but no one asked them the question, what's the probability of being successful in that mitigation? So you need to include the probability as well. And then I want to reiterate that the SIPmath is free and can add distributions of activities or costs. So let's look at a case study of building a house. And what we've done here is we're going to evaluate the house from here, from selecting the contractor until we are sheltered over here. And we've identified all the events that need to happen, and we've shown the relationships. And these lines indicate that, let's say, for example, foundation framing can only be started once we have the land prep and the permit obtained. Okay, that's an example. And then this A goes over to here, this A goes over here as well. Okay? So the data input by the user. You can see we've got P10, 50, 90, so we're going to be using the Myerson distribution in all of these. We're going to get P10, 50, 90s. Here are the tasks that are consistent with the Putt diagram back here that I just showed you. Got all those tasks in there. And we're going to talk about how many days it takes. And also what's the variable cost per day. So based on the number of days here, I multiply by this number. So I'm taking two random variables, going to be multiplying together to get a total cost based on the scheduled days. Plus the scheduled days will impact the scheduled distribution. So once again, we talked about the building graphics. So here we're seeing the results of this analysis, and here's the schedule uncertainty. Here was our reference case. Here's the EV, and this is the current simulation. We're going to be running like 1,000 simulations here. And over here is the building cost. Now, because of the way we set this up, there's a cost of the materials, and then there's the cost for the labor, if you will, from the schedule. And so what we've done here is the labor costs are shown in red, and this is the material cost. So you can see that in this particular case, of this total cost, this is the total cost, the labor cost is the majority of the total cost. Here I'm adding two distributions. And I'm doing this quite easily using SIPmath. Here is our reference case baseline. So now let's play with the live model. Okay, here is the model to build a house. Let me go over the structure of the model to start with. So typically what I do in these models, I use yellow to represent inputs. And in this model, because it's probabilistic, but sometimes it's better to debug the model in a deterministic. So it actually has a use probabilistic yes or no. In this particular case, it's really important to say yes, because that's the whole idea of this project, of evaluating cost and schedule risk analysis. We're going to talk about mitigations. Right now, the mitigations are turned off. Okay. Down here, we see the categories that we talked about in our project on the schedule. And then over in this direction, to the right, we have the cost of labor. And then if I go down a little bit further, well, we have these mitigations, which we'll talk about later. And then we have the cost uncertainties. And in this case, the cost uncertainties, this is for materials now, are aligned with the schedule. But actually, it's not necessary to to have it that way. In other words, the categories for cost could be different for the categories from schedule. And then we also have associated cost mitigations, which may be related to the schedule uncertainties, okay? Depending upon, what is the mitigation that's taking place. So then below that, we calculate deterministic results. These models in SIPmath are really like deterministic models, and then we have multiple trials. And I'm going to show you the trials here in just a moment. And after we run multiple trials, in this case 1,000 of them, we can then calculate probabilistic results. And you can see that to get the average cost of something, I'm simply saying the average is some vector, as it turns out. In this case, this would be the average of the deterministic cost. Well, that vector got defined by SIPmath. Real easy to do. We're not going to go into the how to use SIPmath, actually, how to build the model. I've got lots of different videos on YouTube that you can watch if you want to see how to do that. We're talking about CSRAs now. And then we can come over here to the dashboard. And so the dashboard is kind of a place where, okay, if you kind of get lost in the model, whatever, you kind of come over to the dashboard and you can see all the graphs to see the results. So here we think we've already seen some of these graphs. We've seen the elapsed time, and remember there's two lines here. One's the reference case and one is the current case. And this is our baseline, and here are the costs, right? And then this is a little toggle here where we can change the, see this little yellow line? It moves. Now it's down here, and it moves down here as well. So this gives me different simulations, and there are 1,000 simulations, 1,000 trials. Now the other thing that I've calculated in here is the Gantt chart. So here's the Gantt chart, make it a little bit smaller for you. But it's taken all of the activities and put them in order in which they happen. Actually, I guess it's not quite in the order they happen. I guess it's the way they're laid in, but you can see how they're related here. So design has to be finished before these other activities can start. And I thought there was one that could start a little bit early. Well, these two can start at the same time, framing in wood order. So you get the idea. So this is a really good way to kind of check the input data. Does that make sense looking at the activities? Because one of the things you want to do is you need to really check the logic of this model. And these graphics are designed to do that. Oh, something else I'd like to point out here. Oh, in this particular version of the model, we're also using a Meyerson for the cost uncertainties. Oftentimes we'd use a triangular. That way we can control the lower limit of the cost. But this is a choice of the model or the analyst. So going to the top of the model, up here, I'm showing the reference schedule days, 195.8, and the current schedule days, 195.8. I've made them the same at this point in time. But let's say I'm showing this to the project manager or the decision executive, and he says, well, wait a minute, I understand you talk to subject matter experts about this, but I've done some of I've built a house before too, and we know exactly what the design should be. And I see that you have here a 60 for the P90 design time. That's way too high. I would like to put in here a 45. So what happens if I put in a 45 there? How quick is this going to calculate? Right there, we got it done. So it went from 195 to 191. Well, something else that looks way too long for me is this permit. I know some people down at the City Hall, and we can get that permit through. It won't be a problem. Let's move that to 15. And now we've gone down to 188 days. So we've saved like 7 days here by just making those two little changes. And we started to satisfy the project manager, or the decision executive, that, maybe the changes he's thinking about just don't have the same impact that he thought they would have. And we can talk about that in a little bit. So I'm going to undo those. We'll undo those two changes. So now they're back to the 28 and the 60. And lo and behold, I'm right back to my 195.8. That's the repeatability of SIPmath. The other thing I want to show you over here in the dashboard is we do have an EV tornado chart that can be calculated. And this is showing the impact of each of the activities on the expected value. So this is not a deterministic tornado chart. This is an EV tornado chart. I'm changing one variable at a time, going to the P10 and the P90, and all the other variables are still uncertain. Okay, let me go back to the Excel, to the PowerPoint, and let's look at a few other things. So here are the graphics that I would recommend you show when talking about the CSRA. One is clearly to use cumulative distribution graphs, and we'll use that for both cost and schedule. And if you want to show a probability density function, you can do that. I have some ways of getting this curve to look nice and smooth rather than being some sort of histogram that is very difficult to interpret because the scale is never quite right. And then we're going to have a distribution showing how often each of the activities are on the critical path. And then there'll be a tornado chart here that talks about this EV tornado chart that we showed live over on the model. So here's the EV tornado chart that's been sorted with the element that's most sensitive on top and the ones that are less sensitive on the bottom. And here's the critical path. And what we see is that framing is high on the critical path. It's 100%. It's always on the critical path. Why is it always on the critical path? Well, we can go back to the to the PERT diagram and take a look at that. So here's our PERT diagram. And we can see that framing is where? Here's the house framing. Everything here has to go through this framing. So framing is always on the critical path. At the same time, we see that it's got a high sensitivity. So it has a big impact on our EV schedule. Now, if we look at the window install, it's on the critical path 80% of the time. However, the sensitivity to the EV tornado is quite small. So just looking at the critical path is not sufficient. You need to look at both the EV tornado chart to understand how the EV is going to change and also the critical path. What we can do is take those two variables and put them on an XY graph. So on this graph, we've got the percent of the time it's the activities on the critical path. And over here, we have the sensitivity to the EV schedule. Now, if I look at the top right corner, these are the things that are both on the critical path a lot and have a high sensitivity. We clearly want to work on those and try to find some mitigations. In the bottom right corner, they have high criticality being on the critical path, but less sensitivity on the EV. So what we need to do there is we need to go back to the PERT diagram and maybe see if we can't get them off the critical path, maybe starting things before this activity starts or ends, and somehow eliminate that criticality or at least reduce it. And then we can look at mitigations for this top left quadrant as well. It's going to have less impact. All right, I mentioned earlier this joint confidence level. Well, this is something the government uses, and what they require is a 70% chance of both being under budget and being better than the published schedule. Well, that sounds like a nice goal, nice aspiration. So if I have a CSRA model, I can say, well, if that's what you really want, then let me tell you what the budget number needs to be and how long I'm going to have to give you. I'm going to tell you it's going to take me to develop it. In this case, I need something like a P80 and a P82 on cost and schedule. And that puts 55% of the results of my simulations, 55% of all the simulations. So there's, it was 1,000 simulations, so there's 550 down here in this lower quadrant. Now, I can do trade-offs between cost and schedule, so I could do up here, or I could do down here. So this would be increasing my schedule and reducing the cost. This would be reducing the schedule and increasing the cost. So this is kind of a compromise right here. Try to make them roughly about the same. But you can see this is going to cause you to have a bigger budget and a longer schedule. So what is the purpose of the CSRA? Well, it's to make a decision. So what do we need to know to make a good decision about this project? What's important to move the needle? In other words, what's important to move the schedule? What's important to reduce the cost? What can we do about it? What's the probability of success? So here are the mitigations that we came up with for this build the house. One is we can order the windows sooner. And so where this is, this was 75, 35, 45, 50, 75, we think we can get this down to 25, 40, 60, but we think we can only do that 50% of the time. And there's a little bit of cost associated with that, so there's a burn rate that gets associated with that one. In the framing side, we're going to reduce that framing down to 45, and I believe we're going to do that by doing it off-site, prefab some of the framing. But that comes with a cost as well. So these costs are higher over here than the base case. And framing also has a higher cost over here with the prefab. But we can complete this with a 75% probability. So if I did those mitigations, what is the impact on my cost and schedule? So in this case, the mitigations we did improved the schedule. It went from 195 to 173. And on the building costs, though, you can see that the cost went from the black line, dashed black line, to the green. So we've increased the costs by $15,000. 22-day reduction in schedule for a $15,000 cost. And management needs to make a decision. Is that what they want to do or not? We can go into more detail and do those mitigations separately by playing with those probabilities of being mitigated or not. And we can see how that works. But I'm not going to take the time to do that today. So what are the takeaways from this discussion? Conducting a CSRA is important to good decision quality. We need to work on all of the 6 spokes of the DQ spider. We can conduct the CSRA at any time. Very early in the project will help establish a reasonable schedule for when we might have production or when the apartment might be built. And it may also give us a better idea about the costs as well. We need to be clear on the frame. Are we doing this from conception, from feed, from FID? We need to make sure the subject matter experts understand what they're assessing, not including contingency. Are they estimating the minimum, most likely max, the P10, 50, 90? What are they actually assessing? They need to understand this. So there may be a little bit of statistics that needs to be conveyed to them. And then you want to stand back and look at the CSRA and ask, does it pass the gut test? Maybe look at the Gantt chart. Make sure you got the right relationship of the activities. You want to generate that EV tornado chart? and the CPM graphics to gain insights. You're also going to find out whether this can test your model too, and determine what is important to mitigate, and then frame mitigation options, and then evaluate them. Something else I want to say about the model. From an analyst perspective, always assume there's an error in the model. You're always looking for an error in the model. It's never right. And so be on the lookout for that. So thank you for participating in this presentation. And I hope if you have some questions, that you put those down there, and I will do my best to answer them. You can reach me at brian@theputts.com. I'm also available on LinkedIn. Thank you very much.